Circular motion number 4. So it says it's a golf cart. That doesn't matter. What matters is that it's rolling without slipping. So you have these wheels rolling along the ground. The radius of the wheels is 0.15 meters. They rotate counterclockwise at 8 radians per second. And they accelerate clockwise at 12 radians per second squared. So it's slowing down. What direction is it moving, speeding up or slowing down? And then we want to know the velocity vector of the golf cart, which is the same as the velocity vector of the center of the wheel. And we want to know the acceleration of the golf cart. That's the acceleration of the center. Okay, so the velocity vector, well, first, which way is it going? That's just sort of looking at it intuitively. The direction it's going is the direction of the velocity, which depends on the angular velocity. So if the wheel's going this way, it has to be rolling this way, like what's usually our negative x direction. And since these two are opposite signs, it's slowing down. Yes?
Can the roll cart, like if it's going this, if it's going that, in the bottom, can it go to the right if you go in the bottom? But like on the ground for the cart, for the
Can C go to the right?
No, I mean the bottom, like the bottom of the ground, like can it go to like the right instead of on the top to the left?
Oh, just the arrow?
Yeah.
Yeah, you can draw that anywhere. Okay, so the velocity of the center, or I guess we're going to calculate the speed of the center, is equal to omega r. And that's equal to, so I guess we did it like this. That's equal to 8 times 0.15, which I think is 6 would be 90, 7, 105, 120. So 1.2 meters per second. And then you have to combine that with what you know about the direction. The direction of the velocity is going to be this way. The direction of the acceleration is going to be this way because it's slowing down. And so if we're using this coordinate system, the velocity vector of the center is in the negative x direction, so negative 1.20. And the acceleration magnitude is alpha times r, which is 12 times 0.15, which I think is 1.8 meters per second squared. And that's in the positive x direction, so 1.80 meters per second squared. Any questions about that? Any other homework questions? Okay. Yeah. Yeah, because this is rolling without slipping. So even though the formulas look the same, this is something to make a mental note of. Even though the formulas are the same, this is not circular motion. I mean, to derive those formulas uses circular motion, but this is different than just the circular motion equations. So yeah, so when something's rolling along a flat surface, the acceleration of its center doesn't have any centripetal part. It only has a part that's parallel to the surface. Okay.
Could the windmill have like a center of the circular motion? A windmill.
A windmill, the center of that circular motion is fixed, and so you would do circular motion to calculate accelerations and velocities of the points on the whatever they're called, the blades.
Because it's not rolling enough.
Right. That's totally different. So even though the formulas look the same, or maybe even more because they look so much the same, be very clear to yourself about whether you're talking about rolling or whether you're talking about circular motion. Okay. All right, so let's go back to the example from last time. So the problem was we had two carts that were in contact. And they're free to roll along this flat surface, and there was a 50 Newton force like that applied to the left. And this one had a mass of 20 kilograms, and this one had a mass of 10 kilograms. And the first step was to isolate both carts as a single thing. And then use Newton's second law, and we calculated the acceleration was in the positive x direction, and we're using the usual coordinates. Acceleration is in the positive x direction, 1.6, repeating 0 meters per second squared. And the second thing that we're trying to calculate is we want to calculate the force applied to the 20 kilogram cart by the 10 kilogram cart. Okay, so normally if you're trying to calculate the force applied to a single thing, then that's the thing you isolate. We'll see later that there are some cases where you might want to do it a little differently than that, but that sort of should be the first thought. So if we're trying to calculate a force applied to the 20 kilogram cart, we want to isolate the 20 kilogram cart. So free body diagram of the 20. And the forces can be broken up into two categories. There's a weight force, and then there are contact forces. So let's first figure out what the weight force is. That's 20 kilograms times 9.81 meters per second squared. So that's 196.2 is the weight force. And now we'll go around the boundary looking for contact with the surroundings. Contact with the ground at the wheels. And that's a pushing contact. That if that force wasn't there, then that 20 kilogram cart would sink into the ground. So that has to be perpendicular to the ground toward the chosen body. And I'll give that the variable name N, normal force. And to separate it from the total normal force and the normal force on the 10, I'll write it as N20. And then there's also a pushing contact force applied by the 10 kilogram cart. And you know that's pushing because if that force wasn't there, those two things would merge And so we have a force that's perpendicular to the surface of contact, so it's horizontal toward the chosen body. And you can call that whatever you want, but I'm going to call it R for reaction force. And then on the other side, there's acting on the surface is this 50 Newton force. And now keep going around the boundary. You get back to the beginning again, and so we know we're done. Okay. Yes?
Like if it's a force applied to 20 kilogram by 10 kilogram, which means that the 10 kilogram is giving a force to 20. So that means that resistance to go to the negative coordinate, right?
Well, the way to think about it is, so yeah, you go around the boundary looking for where the surroundings make contact with the boundary. At that point, it's making contact with the 10. So you know there's going to be some kind of force there. And then you have to think, is it pushing or pulling or friction? Well, we know it's pushing because that's the only thing we've talked about so far. But because it's a pushing force, that force is going to be perpendicular to the surface of contact. So it's going to be horizontal, and it's going to be toward the chosen body. Okay? Here's how I want you to think about it. And in your head, your voice should sound like this too. It's like it should be like a human lookup table. Like, okay, like you get here and you're like contact, and then pushing contact, perpendicular to surface of contact. You know, your eyes, like have you seen Terminator? Like you're looking all this stuff up in like digital text in your brain toward chosen body, and then you're done. It doesn't take any thinking, it only takes remembering. You know what I mean? Must kill all humans. Yeah.
For the art, we never consider the force like kind of like reaction, like the.
Well, yes, we would. We would consider that if we were isolating the 10 kilogram cart. But whatever we're isolating, we're only thinking about the forces on that. So, you know, we don't care about forces when we're isolating the 20. We don't care about forces on the 10 because that's something else. You know what I mean?
Okay, so everything that is like kind of pointing toward the body of
Yes.
20, then why do we take the weight like it's pointing like?
Well, you know, there's no reason to. I mean, I could have. So yeah, don't think of it as them going all towards the body because things are going to be different when we talk about pulling forces and stuff. But notice you could move these around so they were all going away from it. I mean, that's just the way I sort of set it up. But pushing contacts, it's always going from the contact toward the body. I guess that's the way to think about it. But, okay, so now Newton's second law. The 50 Newton force is in the positive x direction. So that's 50, 0. The reaction force R is in the negative x direction. So that's negative R, 0. The weight force is in the negative y direction. So 0, negative 196.2. The normal force is in the positive y. Now, every force that's in the free body diagram is represented. So we're done with the left side of Newton's second law. And this is equal to the mass of our chosen body times the acceleration of the chosen body. The mass is 20. And do we know anything about the acceleration of the chosen body? Yep, that's what we calculated in part A. So 1.6 repeating 0.
Maybe 1.67.
Yeah, I don't really care about how you round it off. If you don't round it off at some point, it'll take you a really long time to write it. Okay, so we have two equations. Well, it turns out that what we're looking for is this force R, this right here is the force vector on the 20 by the 10. So we're trying to represent this vector, and if we come up with the variable R, then we're done. So that says that nothing in the y equation helps us at all. You could use the y equation to calculate the normal force. The y equation says 0 plus 0 minus 196.2 plus n20 is equal to 0. We weren't asked for anything about that, so we'll just leave that alone. But now the one that's important is the x equation, and that says 50 minus r plus 0 is equal to 33.3 repeating. And so now just solve for r, and you get that r is equal to 16.6 repeating. And forces are vectors, so you want to give your final answer as a vector. So a force vector on the 20 by the 10, you could write it a few ways. As components, plug the 16.6 repeating into the vector that, as you defined it in Newton's second law. So negative 16.6 repeating 0. Or another way of writing that is negative 16.6 repeating in the direction of x. Or another way to write that is a magnitude of 16.6 repeating newtons pointed in this direction. Any questions about that? Remember that I mentioned this before, and I'll talk about why a little bit later on, but you have a pushing contact between bodies. Whatever body you isolate, that pushing contact is toward the chosen body. So when we isolate the 20 kilogram, that pushing contact is this way. If we isolated the 10 kilogram cart, the pushing contact would be this way, and the magnitude of those two is the same. And so that says if we wanted to know the force vector applied to the 10 by the 20, that would be a magnitude of 16.6 repeating newtons pushing this direction. Any questions about that? Okay, so just thinking about this as sort of an engineering type application, what could you use this for? Well, okay, if those were train cars, that'd be super little trains. But imagine that these are train cars or whatever, they're carrying stuff, and you know that this is the application where you're concerned about some kind of break happening in the walls that are in contact, and you want to use as little material as possible to design these such that these don't break. Okay, so you do this calculation, calculate that force, and then you can use that force to figure out how thick the walls need to be, or is it okay if they're aluminum, or can they have to be steel or plastic or whatever. So that's the kind of thing that this would be used for in an engineering application. You just need this to be sturdy enough to be able to withstand that contact force of 16.6 repeating newtons. Okay. Let's do another example. So this time, let's say that there's a incline. And let's say this angle is 20 degrees. And let's say there's a cart of 50 kilograms in contact with a cart 30 kilograms, and a force applied this way of 500 newtons. So first, what's the acceleration of the system? And second, what's the force applied to the 30 kilogram by the 50 kilogram? So on the 30 by the 50. Okay, so in any kind of rolling or sliding problem, so notice, in rolling and sliding problems, and this is going to be really important when we get to friction problems, use a coordinate system with the y-axis pointing directly out of the surface. Okay, so the coordinate system we're going to use has the y-axis pointing directly perpendicularly out of the surface. That means that the x-axis has to be this way. Okay. It's going to make representing most of the vectors that we're dealing with easier. So that's why we do it. It's going to make one of the vectors we're going to deal with harder. The weight force now is going to be, that's always been easy in the past. It's always just been directly in the negative y direction. Now we're going to have to use some angle and cosine and sine. That's the only one that's going to get more complicated. And that's why we do this. Oh, okay. Okay. All right. So what are we going to isolate first? The whole system. And actually, in a way, like, how could I make this problem trickier? Could have not asked for part A, not asked for the acceleration of the system, and then maybe you'd think like, oh, I'm going to go right into isolating the 30 kilogram cart. In almost every case, you're going to need to isolate the whole system together to first calculate that acceleration, unless the acceleration is given. Okay, and then go into isolating the individual pieces. Okay, so free body diagram of the system. Okay, something like that. So yes, yes, I think that's have to is a strong word, but I would definitely recommend it. I think it'll be a lot clearer to yourself if you do. Okay, and now the first force is the weight force. That's straight down. So that's not, now that's not aligned with the surface anymore. The magnitude of the weight force is the mass, 80 kilograms, times 9.81. So this is 784.8. And now that we've dealt with the weight force, we're going to go around the boundary looking for contact with the surroundings. There's contact at the wheels, and I'll consider that all to be, like, I'll lump it all into a single contact force because these are particles. We're treating these as particles. So that's a pushing force. It's perpendicular to the surface toward the chosen body. And I'll call that N total. Question? No, it doesn't matter. When we start doing rigid body stuff, it will matter. We won't want to lump things together like this. But right now, since we're treating everything as a particle, everything happens at a single point anyways, you know. And the only other force is the pushing force here. That was 200 newtons. Okay, 500 newtons. And no one would say that this is a very carefully drawn picture, but it's careful enough that you can tell that these two are perpendicular to each other, and this is not perpendicular or parallel to these. Okay, well, can you maybe? That's my goal, anyways. That's the goal I want you to have when you draw that stuff. Okay, so when we represent that 500 Newton force as a vector, what's that going to be as components? That's negative 500, 0. Yep, that's why we rotated the coordinate system. The N total, what's that going to be in components? 0 N total. The only one that's a pain is this 784. So let's think about the angle for that one. Let me try to all look like they align. Okay, so here's the coordinate system. And here's the weight force. It has a magnitude of 784.8. And here's an SAT question. What's that angle?
Well, no. Wait. It's basically you have 270 plus 2 be 290.
Right. Well, so exactly. So this angle is 20. That's what I was asking first. And then, yes, what's important is the angle going from the positive x-axis counterclockwise to this vector. And you're exactly right. Theta is equal to 290. You could also do it as negative 70, and it would all work out the same. But so that weight force is going to be 784.8 times cosine of 290, 784.8 times sine of 290. Could someone punch that in to a calculator? That should be, is that the y component? Is that sine? Are you in radians maybe or something?
Oh, it is negative 737.47.
That's wrong too, I think.
I put it on degrees.
Oh no, yeah. It's 441.39.
Wait, what do you mean? I put it on degrees. Supposed to be radians or degrees?
It's supposed to be degrees because that's what we're defining these angles in terms of. Yeah, the y component should be negative and the x component should be positive. 441.39, okay. That's too big.
268.41.
What? Ooh, that sounds more like it. 268. Okay, 268 point what? Then for the y? Okay.
Yeah,
Oh, that's what you had?
that's what I got.
Sorry.
It's okay.
Sorry for not trusting you.
Okay.
Um, so now Newton's second law. So the normal is 0 n total. The weight force is 268.4, negative 737.5. The 500 Newton force is negative 500, 0. And that's equal to the mass, 80, times the acceleration vector. And just like before, we have to figure out what line this is going to move along. Is it going to move along the x-axis or the y-axis? The x. And from this, it's not super obvious right off the bat whether it's going to accelerate in the positive x or the negative x. But like I mentioned before, it doesn't matter. We're just going to write it as a0. And if it comes out negative, then it's going in the negative x direction. Okay. All right, so there's Newton's second law. The y equation we could use to calculate the normal force. But we're not asked for that in this problem, so I'm going to skip it. Notice, though, that this time it's not equal to the weight. Somebody asked a question about that before. A lot of times we will see it equal to the weight, but there's no rule about that. And then the x equation says 268.4 minus 500 is equal to 80a. And so can someone calculate that a value? 895 minus. Okay, so what's the acceleration vector? In our coordinate system, the acceleration vector you get just, we defined our acceleration to be a0. So now just plug in this value of the variable a, and you get an acceleration of negative 2.895, 0. Or in other words, negative 2.895 meters per second squared times I. Or in other words, up the ramp with a magnitude of 2.895. Any other questions about that part? And then for part B, now we're trying to calculate the force on the 30 by the 50. So what are we going to isolate? The 30? Yeah. So the forces acting on the 30 are a weight force. And that's equal to 30 times 9.81, so 294.3. And then there's a pushing contact from the ground that I'll call N30. And then there's a 500 Newton force pushing up the ramp. And then there's a pushing contact from the 50 that I'll call R. The N30, the R, and the 500 are all along axes. So again, the only complicated one is figuring out the components of the weight force. And the angles are all the same. It's just that now the magnitude is 294.3. The angle we want to use here, theta, is equal to 290. So someone punch in for me 294.3 times cosine and sine of 290.
Minus 276.
Okay. And now we can plug this all into Newton's second law. That force R, what's that in vector components? R0, yep. The normal force, yep, 0 and 30. The weight force is what we just calculated, 100.7, negative 276.6. And the 500? Negative 500, yep. 0, yep. And then that's equal to the mass. This time our chosen object has a mass of 30 times the acceleration vector that we just calculated in part A. So negative 2.8950. And again, I mean, there will be problems where you'll be asked for something that you need the y equation for, but we keep having this same thing where the y equation doesn't give us anything that we're asked for. It just says n30 minus 276.6 is equal to 0. But the x equation says r plus 100.7 minus 500 is equal to, what's 30 times negative 2.895? 287?
87.
Oh, 87. Okay, 0.0. And so R then is equal to, can someone calculate that for me? 12.3 newtons. 312. Makes more sense. Okay, so what's the force vector applied to the 30 kilogram cart by the 50? The answer to that comes from the fact that we know this is the force on the 30 by the 50. And so now we just plug this variable value back into that vector. And you get that the force on the 30 by the 50 is equal to 312.30. Which is equal to 312.3 newtons times I. which is equal to a vector pointing this direction with a magnitude of 312.3. Any questions about that? Okay, so now let's talk about pulling forces. So here's our inventory so far. Our inventory of force directions. Types of forces that we know the directions for are the weight, pushing contact, pulling contact, which we're going to imagine is always involving cables. Even when it doesn't, you could replace it with a cable, so we'll still think of it that way. Friction, and spring forces. And we're done with weight. Now we're done talking about pushing contact. And so we'll go on to pulling contact. And we're always going to think of this as involving cables. Because, like, for example, if I'm pulling this cart this way, the contact between my hand and the cart, the way pulling works, you could replace that with a string or a rope or whatever. You could replace it with a cable. So we'll just always think of it that way. Okay. So pulling contact, when you recognize it is pulling contact is keeping two objects from moving apart. And so, for example, with this, we could do problems similar to the one we just did, but now these two things are connected by a cable, and the external force is pulling them this way. Yes.
So we said there's a condition that the cable is not elastic.
Yeah, for now we are going to say that. Yeah. So these are inextensible cables.
Make a big difference.
If it was, it could make a big difference possibly. If you had an elastic cable, in most cases, you would just treat it like a spring. Okay, you could treat it as a pretty stiff spring, and then it wouldn't stretch that much when you applied attention to it, but it would stretch a little bit. And the direction of a pulling force is parallel to the cable. And this time, with pushing contacts, the force was toward the chosen body. This time it's away from the chosen body. Okay, so as an example, let's say we have two carts connected by a cable. Let's say this one is 5 kilograms. This one's 10 kilograms. And we're applying a force of 20 newtons. And we want to know what's the force applied to the 10 kilogram cart by the cable. Okay, what do you think the first step is going to be? Yep, so we'll isolate the whole system together and calculate the acceleration. There's a weight force of 15 times 9.81, so that's 147.15. There's a combined normal force pushing from the ground, so that's toward the chosen body, and I'll call that N total. And then there's the 20 Newton force here. And we don't have to worry about that cable force yet because that's inside. It's part of what we're isolating. So that's not happening at the boundary. Yep. Just because I didn't ask for it. Like if I had made a part C that said, what's the normal force acting on the wheels of the 5 kilogram cart, then you'd want to calculate the N5. So Newton's second law says negative 0 plus 0 N total plus 0 negative 147.15 is equal to the mass times the acceleration vector. How are we going to represent the acceleration vector? What do we know about the motion? It's horizontal, so it's along the x-axis, so we'll just write that as a0. Even though we can easily see in this case that the acceleration is going to be negative, that negative will just come out on its own. So y, we don't care that. The equation says negative 20 is equal to 15a. So a is equal to negative 1.3 repeating meters per second squared. This is the acceleration vector. Once we fill in that variable a, so the total acceleration is negative 1.3 repeating 0. So now we're about done, but let me at least draw this free body diagram. Now we want to calculate the force applied to the 10 by the cable. How are we going to isolate the 10? So a free body diagram of the 10 kilogram. There's a weight force of 10 times 9.81. There's a normal force N10. And then the last force is that pulling contact from the cable. It's parallel to the cable away from the chosen body, so that force is this way. And I'll write it with a capital T for tension. Any questions about that? Okay, so Newton's second law says negative T0 plus 0, negative 98.1 plus 0 n10 is equal to 10 times the acceleration vector. And so the x equation here says T is equal to 13.3 repeating newtons. Okay, one more thing, and this is really the end. So notice, as long as the cable is massless, which we're always going to make that assumption, and between the two endpoints, it only touches massless and frictionless pulleys. We're also going to make those assumptions about pulleys. The cable tension is the same at any point, at every point along the cable's length. Along its length. So in other words, if we isolated a 5 kilogram cart and calculated the tension on the cable at that contact, we'd get the same thing. Okay. So it's sort of equivalent to that idea that in a pushing contact, if two things are pressing against each other, the contact force on one is equal and opposite to the contact force on the other one. Okay, that's all.